Okay, so we continue on the last case for the estimating the mean from the two samples. That is for the case of paired observation. Okay, paired observation occur when we have two samples and we have the mean from that two sample. It is related to each other, so means that we have a paired observation. So in this case, what we want to estimate is that we want to estimate the mean for the difference between the two means. That is denoted by mu d. So mu d is equals to mu1 minus mu2, the mean from the two samples. So the confidence interval formula that we can consider in this case is this one. So what we have for the point estimator is that we have d bar, and then the critical point we consider the t distribution, which means that this confidence interval is valid for the small sample case. And of course, we need to know the standard deviation for the d, that is the difference. Okay, so to find what is d bar, it is by using this formula. Okay, but then this is actually wrong. This is not mu d. Mu d is the one that we want to estimate. So this is supposedly summation of di. Okay, that is the summation of the difference between the two observation or the pair observation. So divide by n to find what is the d bar, and this is the standard deviation for the difference. Okay, so we go directly to the example. Okay, in this example, if you look, we have 20 observation, 20 number of observation, that is dn. Okay, so you need to find 95% confidence interval for mu1 minus mu2, where mu1 and mu2 represent the true mean for the TCDD levels in plasma and in fat tissues respectively. So assume the distribution of the difference to be approximately normal. Okay, so in this table what we have is okay, we have the observation, the first observation, TCDD levels in plasma, and the second observation, TCDD levels in fat tissues, and di is the difference between these two pair observation. Okay, and then we have 20 observation. So the first thing we need to know from all this statement, in order to construct the confidence interval, we know that the n is 20. And since we want to consider the t distribution, of course we need to know what is the degree of freedom. So degree of freedom is v equals to n minus 1, that is 20 minus 1 is 19. Okay, and then we need to find what is d bar first. So d bar is equal to the summations of di over n. Okay, di over n, summations of di over n, it is given here. We have the list for di, so you need to sum up all this di. Okay, if you sum up, you would obtain that the summations of di is negative 17.4, and then divide by n, that is 20. So this, if you calculate, you get negative 0.87. Okay, so d bar is negative 0.87. Then we find for SD, the standard deviation for the difference. So the standard deviation is 1 over n minus 1, that is 19. So summation di minus d bar square. So di, the first difference is d1, that is negative 2.4. So we have negative 2.4 minus d bar. Okay, minus d bar is negative 0.87. Okay, and then you square. Okay, and then plus the second difference, that is d2. d2 is negative 2.8 minus negative 0.87 square. Okay, and then plus the third one, negative 2.3 minus negative 0.87 okay, plus so on until the 20 observation. Okay, if you calculate this as t, it will be eventually equal to 2.9773. Okay, so now you already have the d bar and the standard deviation d. So we want to find 95% confidence intervals, means that the alpha would be 0.05 and alpha over 2 is 0.025. Okay, so the t alpha over 2 that you want to find would be for t 0.025. So if we construct the bell shape, so t 0.025 would be at the positive side. Okay, to find what is the point for the t 0.025, we know that if we use the t distribution table, if we want to find the area for this one, okay, it would reach from this point to the right. So means that you know that this area is 0.025. Then if you look inside the table for the area 0.025, you will obtain the point, this point for t 0.025. So we check on the t distribution table. Okay, so 0.025, so it is this one, 2.093. So this one is 2.093. Okay, now you can plug in everything inside the confidence interval formula. So we have d bar negative 0.87. Okay, minus the t alpha over 2. T alpha over 2 is 2.093. Multiply with SD. SD is 2.9773. Divide by set n, that is set 20. Okay, less than mu d. So for the upper bound, we should obtain the same thing, but we should consider plus instead of minus. Okay, so I copy this one. Okay, buat ke atas sikit. Okay, this is plus. Okay, so mu d. Okay, if you calculate, mu d would be in between 0.5234. Okay, and the lower bound is negative 2.2634. Okay, so this is the confidence interval for 95%. Okay, if you look at this confidence interval, it is between negative 2 until 0.5 roughly. So within this interval, we have the point, we have the value of 0. Okay, 0. So means that somehow maybe mu d would be equals to 0 because 0 is within that interval. Okay, if mu d is equals to 0, it means that when mu d is equals to 0, and we know mu d is mu1 minus mu2. Okay, so mu1 minus mu2 also be equals to 0. So if we have mu1 minus mu2 equals to 0, then it is mu1 would be equals to mu2. Okay, so from this we can make a conclusion that okay, since 0 is inside the interval, Okay, so means that mu1 equals to mu2. This means that these two means has no difference. Okay, so there is no significant difference between the two mean. Okay, so this is the conclusion that you can make from the confidence interval. Alright, so this is for the part observation when we have when we want to estimate the mean from the two samples. Okay, then we go to the estimating the proportion for the case of single and two proportion. Okay, so for this single and two proportion, we consider for the case of large samples. Okay, so what we have here, we want to estimate what is the P, that is the proportion. So the point estimator is P head, and since we want to consider large samples, then we consider the Z distribution. So we have P head, Q head. So you know that if P head, the Q head would be 1 minus the P head. Okay, so in this case, we have two types or two method for the confidence interval. This is the first one and this is the second one. So the second one is a bit complicated and tedious for you to calculate, so I would prefer to use the first one, but you can try both. Okay, we look at this example. So in a random sample of N500 families owning television sets in the city of Hamilton, Canada, it is found that X equals to 340 subscribes to HBO. Okay, find 95% confidence interval for the actual proportion. Okay, all families with television sets in the city that subscribe to HBO. So in this case, you know the N is 500. Okay, and X is 340. So since this is regarding proportion, so P head is 340 divided by 500. Okay, so this is equal to 0.68. Okay, you know P head, then you can find what is Q head. Q head is 1 minus P head. Okay, that is 1 minus 0.68. This is equal to 0.32. Okay, so you want to find 95% confidence interval, the same as previous example. We have alpha 0.05 and alpha over 2 is 0.025. So the critical points, we use the Z. So means we have Z alpha over 2, Z is 0.025. Okay, if you construct just to illustrate, so this is Z 0.025. Okay, so since this is the Z table or the normal curve distribution, so it is easier for us to find the Z from the negative side. Okay, because for the Z table, we read for the probability or the area, it is from the points to the left. So it is easier for us to find this point that it will be eventually equal to the positive sides lah. So this part, if we find the area in this part, that is 0.025, you would obtain this point for negative Z 0.025. Okay, so you check for the normal curve distribution table, 0.025. So the area is inside the table, so the point is the outer parts. So 0.025 located at 0.025, 0. Okay, this one. So it is negative 1.96. Okay, which is this is negative 1.96. So since this is for the negative part, so automatically for the positive Z, this is also 1.96. Okay, that covered. Okay, okay, so we can construct the confidence interval. So we have P hit we have calculate that is 0.68. Okay, minus the Z alpha over 2, 1.96. And then multiply with the set P hit multiplied by Q hit over N. Okay, P hit 0.68 multiplied by Q hit 0.32 divided by N, which is 500. Okay, this is less than the proportion, the true proportion. Okay, so the upper bound is actually the same thing but with plus. Okay, so this is plus. So if you calculate, the P is in between 0.7209 okay, and 0.6391. Okay, so this is the confidence interval, about 95% for the proportion. Okay, and this is by using the first method. Okay, you can try to construct by using the second method. You would get almost the same confidence interval. If you try to find for using the second method, you obtain that the P is in between 0.7194 and 0.6378. Okay, it is actually almost the same lah, approximately, compared to the first method. Okay, you can try to find. Okay, another statement, we have another formula here. So it says that P head is used as an estimate of P. We can be confident that the error will be less than the specified amount E when the sample size is approximately equals to this one. So when you have the error and when you have the P head and Q head, so you can find what is the suitable sample size, okay, or the N. Okay, so for example, how large a sample is required if you want to be 95% confident that our estimate of P in the previous example is within 0.02. So 0.02 is the E, the error. So you can just plug in all the information to find the largest sample that is required. So N equal to Z alpha over 2 square. So Z alpha over 2 previously is 1.96. Okay, P head is 0.68. Q head is 0.32. Okay, divide by E, which is the error. So it is given that the E is 0.02 square. Okay, so if you calculate, this one is equal to 2089.8. Okay, so this can be round off. So it is approximately equals to 2090. Okay, so the size of the samples that we can have in order to be 95% confidence interval that the sample proportion will not differ from the true population by more than 0.02. Okay, I wrote the conclusion here. Okay, if we base our estimate of the proportion P on a random sample size of 2090, we can be 95% confident that the sample proportion will not differ from the true population not population, proportion by more than 0.02. Okay, next formula we have also for the case when if P heat is used as an estimate of P, we can be at least how many percent confident that the error will not exceed the specified amount of E when the sample size is given by this formula. So the difference is that this is for the case when we want the confidence interval to be at least by how many percent. Okay, the previous one is just that the exact percentage of confidence, but this one is for the case when to be at least how many percent confident. So the same thing, we can apply the given formula. So by using the previous example, okay, so how large a sample is required if you want to be at least 95% confident that the estimate of P in previous example is within 0.02. So the same thing, you can find the sample size. So n equals to 1.96 square divided by 4, 0.02 square. Okay, so you can calculate this one. It will be equal to 2401. Okay, so the sample size is 2401. And we can make a conclusion. We can say that based on this, okay, if we base our estimate of P, the proportion, okay, on a random sample size of 2401, we can be at least 95% confident that the sample proportion will not differ from true proportion by more than 0.02. Okay, so that is how we can conclude based on the calculated sample size. Okay, next for the confidence interval for two samples of proportion, means we have two proportion from two different samples. So to construct the confidence interval, in this case we consider for the large samples. Then what we have for the confidence interval formulation is that, of course, we have the point estimator for the true proportion P1, P2 is P1 hit and P2 hit. Okay, so if you want to estimate for P1 minus P2, then the estimation or the estimator would be P1 hit minus P2 hit. Okay, if it is the other way around, then it should be tally lah with the true proportion with the point estimator. So since it is for the large samples, then we consider Z distribution. And we also need to know what is the Q hit 1 and Q hit 2 to construct for the standard error terms. Okay, we look on the example. Okay, so a certain change in the process for manufacturing component parts is being considered. Samples are taken under both the existing and the new process. So you know there are two cases, that is existing and the new process. So we consider there is two samples in this case. So if 75 of 1,500 items from the existing process are found to be defective, okay, and 80 of 2,000 items from the new process are found to be defective. So find 90% confidence interval for the true difference in the proportion of defective between the existing and the new process. So from this statement, okay, we know we can divide it into two. That is for the existing process and also the new process. Okay, for the existing process, we have 75. That is the X1 is 75. Okay, and N1 is 1,500. Okay, so the P hit is X1 divided by N1. Okay, that is 75 divided by 1,500. So it is equals to 0.05. Okay, for the new process, we have X2. Okay, X2 is given by 80. Okay, and then N2 is 2,000. And then you can find, okay, this is P hit 1. You can find the P hit 2. That is 80 over 2,000. And this is equals to 0.04. Okay, so you know the P1 hit and P2 hit. So from that, you can find what is the Q1 hit. Q1 hit is 1 minus by the P1 hit, that is 1 minus 0.05. So it is 0.95. Okay, and the Q2 hit is 1 minus 0.04, the P2 hit. It is equal to 0.96. Okay, and then you want to find 90% confidence interval, means you have alpha is 0.1 and alpha over 2 is 0.05. So the critical point involved is you want to find Z alpha over 2. So Z alpha over 2 is Z 0.05. If we illustrate, okay, to find what is the point for Z 0.05. Okay, since it is a Z table, to make things easier, we find from the negative side. So we can find directly, that is, this is the point negative 0.05. So if we find the area for this, the area for this one, which is the area for 0.05, you will directly find what is the point for negative Z 0.05. Okay, we check the Z table for 0.05 where it is located. So check inside, since you want to check the area is inside the table, 0.05. Okay, so it is in between these two. Okay, so we take the value is negative 1.6, 1.6 4, 1.645 in between lah kat sini. So 1.645. So this is equal to negative 1.645. Okay, since this covered the same area, so for the positive side, this is 1.6445 for Z0.05. Okay, so you can plug in this inside the confidence interval formula. So P1 head minus P2 head is 0.05 minus 0.04. Okay, minus Z alpha over 2, that is Z 0.05, that is 1.645. Okay, multiply with the surd P1 head multiplied by Q1 head, that is 0.05 multiplied by 0.95 divided by N1. N1 is 1500 plus P2 head multiplied by Q2 head. P2 head is 0.04 multiplied by 0.96 divided by 2000. Okay, this is less than P1 minus P2. Okay, so I continue here lah. Okay, for the upper bound, it's just the same with the lower bound, but we have plus in between. So I just copy. Okay, so this one is plus for the upper bound. So if you calculate this one, you will obtain that the proportion P1 minus proportion 2, it is in between 0.0217 and negative 0.0017. Okay, so this is the confidence interval, 90% confidence interval for the difference between the two proportion. Okay, and then okay, the last part, this is about estimating the variance. So we have seen on to estimate the mean and also the proportion. This one is estimating the variance. So when we estimate the variance, you know that the involved table distribution is actually chi-square and also the F distribution table. Chi-square is for the case when you have a variance from one sample, and then we consider the F distribution when we have two variants from the two samples. Okay, so we go first on the single sample for the estimating the variance. Okay, so if S square is the variance of a random sample, so we know that S square is the point estimator of size n from a normal population. So a confidence interval for the variance from the true population is given by this formula. So from this formula, what you need to have is that you need to know what is the n, okay, the sample size, and you need to know what is the variance from the samples. Okay, and since we apply the chi-square distribution table, then we need to know what is the degree of freedom. So degree of freedom is the sample size minus by 1, that is V equals to n minus 1. So we go directly to the example. Okay, in the example, it says that the following are the weights in decagrams of 10 packages of grass seed distributed by a certain company. So you know that the sample size is 10, so n is 10, and you are given a data instead of the direct variance. Okay, so you need to construct yourself the variance by using the data. Okay, and then you need to find a 95% confidence interval for the variance of the weights of all such packages of grass seed distributed by this company, assuming a normal population. Okay, so we know that in this case n is 10. So from the n, we know the degree of freedom is 9. Okay, and then we find what is the variance for the samples, that is the S square. Okay, so there are two formula to find the variance for the sample. The first one is you can use this one, 1 over n minus 1 multiplied by the summation of xi minus x bar, and then you square. Or you can also use another formula, that is 1 over n minus 1 multiplied by n summation of xi square minus summation of xi, and then you square everything. Okay, so in this case I would prefer the second one. Okay, so you can find the variance for the sample. So 1 over n is 10, so n minus 1 is 9. Okay, multiply by the n, which is 10, multiply with the summation of xi. So you summation of xi square. So means that you sum up, that is 46.4 square plus 46.1 square plus 45.8 square, and so on. So you will get this is equal to 21273.12. Okay, and then minus the summation of all the data, and then you square the all of the summation. So the summation of xi would be 461.2. Okay, and then you square. Okay, so you get the variance for the sample is 0.286. Okay, you want to find 95% confidence interval again. So means that alpha is 0.05 and alpha over 2 is 0.025. Okay, so we use the formula. So we have n minus 1, that is 9, and then s square we have calculated, that is 0.286. Okay, so this one divide by chi square 0.025 for alpha over 2. Okay, less than the variance, less than 0.286 divide by chi square. Okay, please notice this one, chi square 1 minus alpha over 2, so we have 0.975. Okay, so this one we can simplify, we can rewrite as, okay, so you check inside the chi-square table for the case when alpha is 0.025 and degree of freedom is 9. So you check chi-square table 0.025. Okay, this column, and V, degree of freedom is 9, so it is 19.023. So 19.023 less than variance. Okay, check also for 0.975. 0.975. Okay, this column, and V is 9, so you have 2.7. Okay, if you calculate this one, you'll be the variance would be 0.953, and this is 0.135. Okay, so this is the confidence interval about 95% for the variance. Okay, this is for the one variance case, and then we go for the case of two variance, that is in the form of ratio. Okay, so in this case, of course, we have 2-point estimator for the variance, that is S1 square and S2 square, and also have 2 samples, N1 and N2. So the confidence interval is given by this formula. So you need to know what is S1 and S2 to construct. Okay, for the degree of freedom for the first samples, it is V1 equals to N1 minus 1 and V2 N2 minus 1. Okay. Okay, for this derivation, you can just take a look for your own information. Okay, so we go to this example. Okay, so a confidence interval for the difference in the mean orthophosphorus contents measured in milligrams per liter at 2 stations on the James River was constructed. We look at the previous example that we consider on the case of unknown and unequal variance for the estimating the mean. Okay, previously you check back. Okay, by assuming the normal population variance to be unequal, so justify this assumption by constructing 98% confidence intervals for the ratio between the first variance divided by the second variance, and also for the standard deviation from the population. Okay, so where the variance 1 sigma 1 square and sigma 2 square are the variance of the population of the orthophosphorus contents at station 1 and 2 respectively. Okay, I have extract the information. Okay, that is this one. We have 2 stations, we have 2 samples. So we have 2 degree of freedom, and also we have 2 standard deviation from the samples. Okay, so from this one, we want 98% confidence interval, means we have alpha 0.02 and alpha over 2 is 0.01. So we can apply this formula. So we have S1 square. S1 square is 3.07 square divided by S2, and then V square 0.8 square. Okay, multiply by 1 over F alpha over 2, that is F 0.01, with degree of freedom is 14 and 11. Okay, this is less than the ratio. Okay, and then this is the same thing. Okay, and at the upper bound, it has different kind of the critical point. So it has F alpha over 2, that is F 0.01, and this degree of freedom, it is twisted, so it is 11 and 14. Okay, so you need to check the F distribution table for this one. Okay, what is for the case when F 0.01, degree of freedom is 14 and 11. Okay, so we check the F distribution table. Okay, for the case 0.01, this is 0.05. 0.01 when V1 is 14 and V2 is 11. If you look at this table, 14 is not inside. Okay, but we have is 12 and 15. Okay, but what we can do is we just make approximation. So V2, we have we want to check for V2 11. So we look at this column. Okay, so 14 is in between this part, 12 and 15. So between this 12 and 15, we know we have 13 and 14 in between. Okay, so 14, so for 12 we have 4.4 and 15 is 4.25. So how to find for the 14? Okay, in between this we have 13 and 14. So to find, to estimate, to approximate the point for 14 between these two, what we can do is we find the difference between these 2 points of 15 and 12. So when we minus 4.4 minus 4.25, the difference within these two is 0.15. Okay, to find for the case of 14, what we can do that we know that the difference from 12 to 15, the subinterval would be 3. Okay, so 0.15 we divide by 3. So we know that the distance between 12 to 13 is 0.05 and 13 to 14 is 0.05. So this distance, check please, the distance from 12 to 13, 13 to 14 and 14 to 15 is 0.05. Okay, which means to find what is 14, okay, 15 is 4.25, which means that we need to add 0.05 to 4.25. So 4.25 plus 0.05 is 4.3. So which means for 14, we can approximate it to be 4.3. Okay, so we use that value. Okay, so this is 1 over 4.3 less than the ratio of the variance. Okay, and then you check for the F alpha 0.01 and 1114. Okay, this one I think you need to approximate as well because there is no 11 inside the F. Okay, so V1 we check for 11. 11 we know it is in between 10 and 12. It is somewhere here, just in between. And then we look at the 14, this part. So 10 we have 3.94 and 12 we have 3.80. So we check the distance between these two. So 3.94 minus 3.8, then you get 0.14. This is the distance. So you want to find for 11. 11 dekat tengah, in the middle. So 0.14 we divide by 2. So we know the distance between 10 to 11 is 0.07. And the distance from 11 to 12 is also 0.07. So to find what is for the case of 11 means that we can either 3.94 minus 0.07 or 3.8 plus by 0.07. So 3.8 plus 0.07, then we get it is 3.87. Okay, so for 11 we have 3.87. Okay, so this is 3.87. Okay, so you can calculate for the ratio. This is in between 56.991 and 3.425. Okay, this is for the ratio for the variance. Okay, the first one. Okay, the second one you need to find for the standard deviation, radiation for the standard deviation, which means we can square both sides, square all the terms. Okay, if you square 3.425 square root, and this one if you square it you get sigma 1 divided by sigma 2, and this is square root 56991, and you will get the ratio for the standard deviation is 7.549 and 1.851. Okay, so this is the confidence interval for the ratio for the standard deviation, and this is for the ratio of the variance. Okay, for the ratio for the standard deviation, what can you conclude based on this? Okay, since we look at this interval, there is no value of 1 included because it is from 1.851 until 7. So 1 is not included inside the interval. Okay, which means that the sigma 1 divided by sigma 2, the ratio is not equal to 1. Okay, when it is not equal to 1, from this one, you can also rearrange. It is actually sigma 1 is not equal to sigma 2. Okay, so in this case, it also means that the variance 1 is not equal to the variance 2 also. So if you look at the example back, it is true that the variance is unequal. Okay, and we have proved it from this estimation for the by using the ratio. Okay, so it is true. Okay, so that's all. This is for the variance from the two samples. Okay, so from this chapter, we have in total how many confidence interval? Okay, we have in total, okay, we have 3 confidence interval for estimating single means. Okay, and then we have 4 for the estimating 2 means. We have 2 here and 2. Okay, so you to make it easier for you, I recommend to make a list for all of these formula of confidence interval. Then you can see what is the difference between all of this. Okay, and you just need to apply the formula based on the given statement. So you need to know how to extract information, and you need to know which one of the formula for the confidence interval that you need to construct. Okay, so that's all for this chapter, and this chapter will come out for your final exam. Okay, not for test 2 yet. Okay, so that's all for this one, and thank you.